So in this video, we're going to discuss the concept of Le Chatelier's principle and how to apply it in many different ways that we could stress a reaction. So let's say we have a reaction here. Nitrogen gas reacting with hydrogen gas is in equilibrium with ammonia gas, NH3. If this is at equilibrium, we know that the forward rate is equal to the reverse rate. And we know the concentrations of the reactants and products are remaining constant over time. However, if we stress this reaction, meaning if we do something to it, the reaction won't be at equilibrium anymore. But what Le Chatelier's principle describes is the system. This system will shift itself. It will adjust itself to get back to equilibrium by changing the concentrations of reactants and products. So before we figure out how to predict those shifts, let's talk about the ways that a reaction could be stressed. So there's 4 different ways a reaction could be stressed. Number 1, you could change the concentration. So that's like saying we're at equilibrium and then we add some N2, or we take away some H2, or we add more NH3. We're changing the concentrations. That's going to make the reaction not at equilibrium anymore. We could also change the temperature. We could either heat it up or cool it down. Doing that's going to affect the reaction. We could also change the pressure. We could increase or decrease the pressure. And finally, we could also change the volume. If we change the volume of the system, if it's gases, then that's going to affect the system as well. So these apply for systems with gases only. We can use Le Chatelier's principle kind of in 2 different ways. We can use it quantitatively or qualitatively. Quantitatively would involve using ice tables, which we've practiced a little bit and we'll get more practice with going forward. But you would have your initial concentrations, we would know the change, and we could predict the new equilibrium concentrations. So quantitatively, we could use an ice table. Qualitatively is what we're going to practice today and in class. This is what we're going to use is that little seesaw analogy, where if a reaction is at equilibrium like this, and then we stress it so it becomes like so, how is the reaction going to adjust to get back to being at equilibrium? So we'll talk about those examples in class, and we're going to focus in this video on qualitative predictions using Le Chatelier. So, first way that we could stress a reaction is by changing the concentration. Remember, triangle means delta, which means change. So here's a system, let's say it's at equilibrium. And then let's say we add some N2. We add extra nitrogen gas, N2. Okay? Well, if we do that, the analogy is, okay, we're in a seesaw, we're at equilibrium. Okay? But now we've added N2. We have too much of the reactant side. So again, this is like our reactants, this is our products, this is kind of like your arrow. So if we have too much reactants, now this side is going to be heavier. So now we're not at equilibrium anymore. So the idea is, what is the reaction going to need to do to get back to equilibrium? To make the seesaw kind of go back to where it was, we're going to need to make this side heavier. The way we make a side heavier is by making more of that compound. So we're going to need to make more products. Where are we going to make the products from? From the reactants. So this reaction is going to need to shift to the right. Shift right. What does that mean? That means that the forward rate will increase. So the rate at which reactants turn into products, this rate of the forward reaction is going to increase until we get back to being at equilibrium. So the language that we would need to use, what you would need to be able to do is, if I added N2, what way will the reaction shift? You would need to be able to say that it would shift to the right. Another way of saying that you need to be familiar with is that the forward rate will increase. Or another way of saying that is the concentration of products of NH3 will increase as well. In addition to adding a compound, we could also remove a compound. So let's say we removed some H2. So if we remove some H2, and this is a place where students get tripped up a lot. We're at equilibrium, now we remove H2. H2 is on the reactant side. So I have less H2. So my reactant side is now going to be lighter. I have less of it. So what the seesaw would look like would be like this. Because this side is lighter, so it's going to go up. So in order to get back to equilibrium, I need to make the reactant side heavier again. So the reaction is going to shift to the left. This reaction would shift left. Another way of saying that, the concentration of reactants will increase, or the rate of the reverse reaction will increase. We could prove this quantitatively also using the value of K and Q. So for example, if we added N2, Q is equal to NH3 squared over N2 times H2 cubed. So if we're at equilibrium, Q is equal to K. But let's say we added N2. That's going to make the denominator much bigger than it needs to be. If the denominator is too big, that's going to make Q too small. So to make Q bigger again, I'm going to need to increase the numerator. I'm going to need to make this value larger. To make this value larger, I need to make more products, which is shifting right. So I could prove it quantitatively as well, but for now, what we need to focus on is kind of the seesaw, this analogy here. We could also change, and what would that look like graphically? Excuse me. So we have that same reaction from before, N2 plus 3H2, equilibrium with 2NH3. If we add more H2, the graphs that you'll see is we assume, this is when it's added, that it's an immediate jump. Assume that it's an immediate jump. So if H2 is added, that's more reactant, so this reaction is going to shift to the right. How can we tell that that's true? Okay. Well, look what happens to the amount of NH3. After that H2 is added, the amount of NH3 increases until we get back to equilibrium again, which makes sense with our shifting right prediction. We'll analyze these graphs in class a little bit more. But for now, what about changing temperature? So for changing temperature, you need to know one thing. You need to know, is the reaction endo or exothermic? So quick refresher. When delta H is less than 0, exo. When delta H is greater than 0, endo. So if delta H for this reaction, let's say, is 50 kilojoules per mole, that means that this reaction is endothermic, which means I want you to add the word heat to the reactant side. Endothermic means heat is a reactant. Exothermic means heat is a product. Now we treat the word heat just like it was a compound. So let's say the stress that we do is we increase the temperature. What effect is that going to have? Well, if we increase the temperature, that's adding more heat. Adding more heat is adding more reactants. So adding more reactants is going to make our seesaw look like this. We have too much reactants now. So to get back to equilibrium, I'm going to need to turn some of those reactants into products. So this reaction would shift right. If you decrease the temperature, it would be the opposite. That's just like removing heat. So the equilibrium expression here would go here. Because now we have less reactants than we did before, so this reaction would shift left. So again, key idea, you need to know your endo-exo, and you need to know that you need to add heat as a reactant or a product, depending if it's endo or exothermic. Third change, pressure. This rule, no seesaw. There's no teeter-totter rule for pressure. All the rule for pressure is if you increase pressure, the reaction shifts towards the side with fewer moles. And the opposite is true, okay? If you decrease pressure, we shift towards the side with more moles. And I should add of gas. Of gas. So for example, if we increase the pressure of this system, we know that's going to shift to the side with fewer moles. So we got to think about how many moles do I have on each side. Where do I get the moles from? The coefficients. So I have 2 moles of product, and I have 3 plus 1, I have 4 moles of reactant. So if I increase the pressure, this would shift the reaction, this reaction, to the right, because that's the side with fewer moles. If I decrease the pressure, that would shift this reaction to the left, because that's the side with more moles. It's not always going to be right if you increase pressure. It depends on the number of moles. So you got to count the moles. No seesaw. No teeter-totter with pressure. Make a note of it. Last change, volume. And this one's very similar to the one before. Because we know that P and V, pressure and volume, are indirectly related. So, if you increase volume, that's going to lower pressure. And if you lower pressure, it's going to shift to the side with more moles. If you decrease volume and you increase pressure, because they're indirectly related, that's going to shift to the side with fewer moles. So, that's the 4th change you need to know. We'll practice this in class. You need to know these 4 concepts. We'll analyze these graphs as well. And we'll practice with our pen shifts and move on to ice tables.